Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals tangent x. The first thing to do is find the domain. F of x equals tangent x, which is a trig function that has a denominator. Every trig function except sine or cosine has a denominator. And the denominators of the other four can be seen if we write them in terms of sines and cosines. Tangent of x is sine of x divided by cosine of x. And the domain requires that the denominator cannot equal to 0. So here, cosine of x cannot equal to 0. And that means x cannot be any values that make cosine be a 0. On the unit circle, this occurs at pi over 2 and again at 3 pi over 2. That's between 0 and 2 pi, but it continues beyond there, so there's an infinite number of positive x values it cannot be. But it also occurs in the negative realm because on the unit circle, 3 pi over 2 is equivalent to negative pi over 2 if we go clockwise around the unit circle. And pi over 2 is equivalent to negative 3 pi over 2. And on for an infinite number of negative values x cannot be. So the domain of tangent of x is an infinite number of intervals broken up by each of these successive x values that it cannot be. These are each vertical asymptotes because they are what would make the denominator be a 0. So the domain has an infinite number of intervals. One of them is negative 3 pi over 2 to negative pi over 2. Union. Another one is negative pi over 2 to positive pi over 2. Union. Another one is positive pi over 2 to positive 3 pi over 2. Union. And on in both directions. Trig functions have a tendency to have an infinite number of vertical asymptotes if they have any at all. And they also have a tendency to have an infinite number of inflection points if they have any at all. But nicely, tangent is pi periodic. Which means that it repeats itself every pi radians. Another way to write this is f of x plus pi equals f of x. Tangent and cotangent are both pi periodic. The other four trig functions are 2 pi periodic. But what this means is instead of working on the entire domain, which is an infinite number of intervals and may have an infinite number of inflection points, we can instead pick one of the intervals because each of these intervals are pi radians in width because the vertical asymptotes are themselves repeating every pi radians. They are also part of the periodic nature. The usual interval to pick is this one here, though any of them would work. So we can determine everything within this interval of negative pi over 2 to positive pi over 2, and then extend the results to the entire domain using the pi periodic nature of tangent of x. The next thing to do is find all candidate numbers within this interval. We need the second derivative. We will start with the first derivative. The derivative of tangent is secant squared. We can rewrite that as secant of x and then quantity squared to help us for the second derivative. Second derivative will start as a power rule, bring down the power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside. The derivative of secant is secant tangent. We can combine the secants together. Secant times secant will be secant squared, and then times tangent. It's usually best to turn everything into sines and cosines. So the second derivative equals to 2 times secant is 1 over cosine, and then it's squared. Tangent is sine over cosine. We can multiply all the numerators, 2 times 1 squared, which is a 1, and sine x. Altogether we'll make 2 sine x. And we can multiply all the denominators. There's a cosine x squared, and then another cosine x. That will be cosine cubed x. So we have the second derivative written as a single fraction. All powers are positive. So we can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, 2 sine x equals 0. We can divide both sides by 2, and sine x equals 0. And we're only working on the interval of negative pi over 2 to positive pi over 2. So the only place that sine is 0 within there is x equals 0. We can now work with the denominator. The first thing to do is take the cubed root of both sides, since it's cosine cubed. The cubed root and cube cancel each other out. The cubed root of 0 is 0. And so we want to solve for every place that cosine equals 0 between negative pi over 2 and positive pi over 2. It does not include negative pi over 2 or positive pi over 2, which are the places where cosine would have been 0. So there is nowhere else in that interval. And there are none here. So we have one candidate number in the interval of negative pi over 2 to positive pi over 2, and it is x equals 0. We can now draw an interval line, a line representing the interval. It begins at negative pi over 2, though it does not include its round bracket. It ends at positive pi over 2. It does not include it, round bracket. And put any candidate numbers on here. We have x equals 0 is the only candidate number. It splits the interval into 2 separate intervals. And we can now pick a test value in each of these intervals. Between negative pi over 2 and 0, we can pick negative pi over 4. And between 0 and pi over 2, we can pick positive pi over 4. We can now test the concavity by plugging these test values into the second derivative. The version that's written as sines and cosines will be the easiest. The first test value, negative pi over 4, is in the negative first quadrant, which is the same thing as the fourth quadrant on the unit circle. In that quadrant, sine is negative, so the numerator will be a negative times the positive 2, which is still negative, over, and cosine is positive, and a positive cube is positive. So we have a negative over a positive, which is a negative second derivative, which corresponds to concave down. Plugging pi over 4 test value into the second derivative. Pi over 4 is in the first quadrant on the unit circle. The sign is positive, so we have a positive times positive 2 in the numerator, which is positive. And cosine is also positive. Cubed is still positive. We have a positive over a positive, which corresponds to a positive and concave up. So we have concave down occurring from negative pi over 2 to 0. We have concave up occurring from 0 to positive pi over 2. And right at the candidate number of 0, we have the concavity changing from concave down to concave up. So x equals 0 is an inflection point. And we can find a corresponding y-coordinate by plugging the x-coordinate back into the original function. So y equals f of 0, which is tangent of 0, which is sine of 0, divided by the cosine of 0. Sine of 0 is a 0, cosine of 0 is a 1, and 0 divided by any non-zero number equals 0. So it has a corresponding y-coordinate of 0. It's at the origin. So there is the results over the interval of negative pi over 2 to positive pi over 2. We can now extend it to the entire domain by using the pi periodic nature of tangent of x. Each of these x values, which will be every value in these because these are x intervals, and for the inflection point will just be the x-coordinate because the y-coordinate is a trig function. Each of these can be added with the period pi times an integer n. So we have concave down occurring from negative pi over 2 plus pi n, comma, 0 plus pi n. We have concave up from 0 plus pi n to pi over 2 plus pi n. And we have inflection points at 0 plus pi n, comma, and then 0 y-coordinate is from a trig function. It's not an x, so it does not have a pi n added onto it. Where n is equal to any integer. It can be a positive integer. It can be a 0, which will put it into the interval that we worked on. And it can be a negative integer. And this will give the entire results over the entire domain of tangent x.